But we've got some two very exciting speakers starting out the session this morning. We're going to begin with Professor Dr. Thomas Schulthess. He's received his PhD in physics from ETH Zurich in 1994 and is a professor for computational physics currently at ETH Zurich and director of the Swiss National Supercomputing Center in Lugano, Switzerland, known as CSCS. Thomas holds a visiting distinguished professor appointment at Oak Ridge National Laboratory, where he was group leader and researcher in computational material science for over a decade before moving to ETH Zurich in 2008. Thomas' current research interests are in the development of efficient and scalable algorithms for the study of strongly correlated quantum systems, as well as electronic structure methods in general. And he is also engaged in the development of efficient tools and simulation systems for other domain areas such as meteorology, climate, and geophysics. Dr. Schulthess will give us a talk today on delivering performance in scientific simulations, present and future role of GPUs and supercomputers. Thank you, Thomas.
Thank you for giving me an opportunity to present our work and discuss our views of GPUs. I guess the naive way of looking at the role of GPUs in supercomputers today is they are accelerator devices attached to the PCIe port and talk to a CPU that is integrated into a large scalable parallel computing systems. And so the question is why make things more complicated than that? Well, what I just said is really hardware-wise is correct, but not the correct view from an application point of view that I will try to convey here. It also makes a lot of people nervous in supercomputing that you have this very fast device that talks to the CPU over the PCIe bus. And so people somehow have the impression this cannot work. But the reality is it does work. It works in systems at scale. And basically what we really have to start with is really ask some deeper questions, or not deep questions, some simple questions about, for example, what exactly do we mean by good performance? You know, isn't it just flops and floating point operations per second? Or is it something else? Well, if you come from an application perspective, the people who do simulations, there's really two things that you have to worry about, namely energy and time. Time, I think, is obvious to most people. You want simulations to finish. Energy turns out, at least for those who do games on mobile devices, they also know if you have a battery and you have the energy stored in a battery, then you have to worry about energy as well. But it turns out even on supercomputers or on any physical problem you try to solve, energy is always the first question. It happens to be the Fourier transform of time, so that it's not surprising that these are the two main things we have to worry about. Well, then comes the question, but then what about flops and gigaflops per watt? You know, are top 500 and green 500 meaningless? If well, it turns out not necessarily. This is now the question of what applications are we looking at. So, for example, if we want to solve a dense linear problem, such as LIMPAC, the LIMPAC benchmark, which is representative of many applications, then you can convince yourself very easily. I guess you can take a matrix multiply, and then you can convince yourself that if you multiply two matrices, you do n to the cube floating point operations, you are dealing with n to the square data elements. So the ratio of what is called arithmetic density of floating point operations to load stores is of order n if n is the problem size. So the bigger the problem, the more computationally intense your calculation. And that means measuring floating point operations is a good metric for the amount of work you do in this problem, these type of problems. And so therefore, normalizing the time to solution with the work, namely the number of floating point operations, is a good way of looking at the problem. And optimizing time to solution, meaning you have to do the inverse, namely FLOPS, floating point operations per second. So that's just the inverse of this here, and that we call performance. So here we have directly a relationship between minimizing time to solution and maximizing FLOPS in these type of problems. For the energy argument, it's very similar. You take the energy and you normalize it by the work that you do, so energy per FLOPS, or joule per FLOPS, and the inverse of it, namely minimizing energy to solution, means floating point operations per joule. And then it happens that you can introduce seconds on both sides here, and then you get floating point operations per second per watt. And that's the metric of Green 500. So for the particular problem of dense linear algebra, the metrics we have in Top 500 and Green 500 are very meaningful. And even though maybe the algorithmic motive may not be the one you use in your applications, there are many in material science, quantum simulations, chemistry that actually use these motifs, and in those cases we have a very good metric with floating point operations per second and flops or gigaflops per watt as a metric. Okay, but we are in a climate session, so we are not looking at this type of applications. I just want to, for completeness and also because I promised it in my abstract, really emphasize that there is a part of the world in simulation science that does very well with these metrics. For climate, we have to look at things differently. And here, most of you, I guess, know things are more complicated. But the question is, are they really more complicated? So what I'm going to try to do in the rest of this talk is convince you that they are actually not much more complicated. But we start with complicated code. So we actually, I made a mistake here. Sorry, this is COSMO, not COSO. The model that we are looking at is named after this Consortium for Small-Scale Modeling. It is a limited area climate model, so it's very similar to WRF with some differences that I will point out. It is used by 7 weather services, the Swiss, Meteo Swiss being one of them, and this is why I'm dealing with this, because we run the simulation systems for them. But it's also used by about 50 universities and research institutes, and this number is actually growing. So it's a sizable type of model and problem in terms of importance that we are dealing with, and so it's a good thing to look at. The way it is used at Meteo Swiss, we have they are really starting from a global model that comes from ECMWF that provides the initial conditions and boundary conditions to a 7-kilometer model that is run over Europe. And then this is fed into a 2-kilometer model that is run over the Alpine region. And it is this one that we have to look at because that's where most of the compute demand is in this production cycle. So it's a real model used for, not the benchmark that we are talking about here, that is used for daily weather forecasting for Swiss air traffic control, and safety management in events of nuclear accidents that we hope never happen, but we have to be ready nonetheless. And a number of other products. So these are just the main ones that we are dealing with. The code itself, the current production code, is of the order of a few 100,000 lines long, the Fortran code, and when you break it up, in terms of lines of code and performance, you will find that about 60% of the time in the production problem is spent in the dynamics, which is 20% of the code. Another 20% of the code is where the other 20% of the time are spent, namely in the physics parameterization. And then there's other things that are less important in time. In production time. So really when we analyze the problem, we have to look at these two. areas. Physics and dynamics, not really surprising. But unlike the material science problems, quantum problems, we don't have hotspots in the code. So the code is really a monolith, few 100,000 lines long, as I said, and the time is spent equally everywhere. And we take code snippets from the physics part and from the dynamics part without going too deep into the algorithms yet, just take the codes and that represent the work in these areas and then look at them, and we find the physics is more or less compute bound. You can count the flops and the load stores here, and the part in the dynamics seems to be memory bound. But we run these snippets now on different processors. This was done actually a while ago, part of the initial analysis. And you find that running, say, if we take the current code as the reference, running on a multi-core AMD Interlagos processor, and then we run these two code snippets on the Fermi processor. At the time today it would be Kepler. You see that we get actually substantial speed up on the physics and maybe a bit less, but still good speed up on the dynamics. And this is really optimized. Both codes are optimal in this case. So we're really comparing apples to apples on different architectures. But you also find that when you include the data transfer over the PCIe bus, then the performance of this GPU breaks down. So really, and this is really where the view of how you view the GPU in such a system becomes very important. Namely, not necessarily where you accelerate compute, but where do you keep the data. That's fundamental to this problem. And that's why I want to get away from this accelerator perspective. Given this understanding, it was fairly obvious that we have to spend a lot of time working on the dynamics. So we pretty much rewrote the dynamics in C++ this time, and we left the physics as is and used OpenACC directives to deal with the physics. And from what I just said on the previous slide, I think it's obvious why we take this view, because here it's easy to make the code optimal because it's compute bound, okay, and it's parallel. Over here, things are more difficult, okay, and I think most people who know climate codes know things are a bit more difficult there, okay. So we dive a bit more into the dynamics. So we have a model that we represent here by a Cartesian grid. The grid spacings are, as I said, they are 2 kilometers in the high resolution case. They may be 7 or 20 kilometers in lower resolution cases in the lateral dimension. And they are of order 60 meters in the vertical. And from a physics point of view or from a mathematical point of view, and the two go always hand in hand, physics and math, it is clear that the shortest timescales we have to resolve are in the vertical direction. And so the way COSMO is solving the PDE on a structured grid, and you can imagine the fields that we are looking at, or the variables are velocity, temperature, pressure, humidity, so very natural things. But the physics is really split we have two time scales we have to deal with. One is the vertical time scales that are given by this very short mesh dimension here. And if we manage to integrate out these short time scales, we are left with much longer time scales for the horizontal advection and integration. And by doing this split, and this is where really COSMO differs from WRF, we can have a long time step in the vertical direction because we take care of all the stiffness problems implicitly through this implicit solve in the vertical direction. So this is very important to make things more efficient computationally, but then they become more difficult to handle from a scalability point of view. Okay, but that's a typical problem we see in computational science often. So assuming we can deal with this implicit integration somehow, I will come back to this, then we are left with finite differences and explicit integration. And finite differences, I just want to remind ourselves, we have a structured data, and the stencils are then really ways to fixed patterns to update array elements. Like here, the Laplacian as an example, the code, the stencil is really you take the differences to the neighboring elements and you update the central element. And you can do this now assuming double precision, and you will see this expression has 5 floating point operations, 6 load stores. That's about 0.1 floating point operation per byte. And if you take Kepler, and actually this I did in the plane, I don't remember, it's 200 gigabytes per second, the bandwidth. 250, okay, so it's a bit better. It's 180 for the streams. That's the one I really care about, the peak. But you can see, no matter, okay, so this number may be a bit lower, but it's still more than an order of magnitude away. And that's why we say, and I iterate it again, we have a bandwidth-bound problem. So the metric instead of flops has to be gigabyte per second that we are looking at. And then the energy metric is somehow related to gigabytes of data moved around. So somehow around that. Now, the reality in the code, in the dynamics, is not that simple, is a little bit more complicated because, as I said, we have 2 motives. We have this implicit integration, tridiagonal solve in the column with loop carried dependencies, and where we have to focus on the k-axis, and then we have the in-plane axis of data for the stencils where we don't have loop carried dependencies. So this one is easy to parallelize everywhere. This one is easy to parallelize as long as you parallelize over columns. But the main point of showing these 2 patterns is that depending on the hardware you're working on, you may want to choose different storage orders, either K first or IJ first. Okay, and that makes things more complicated from a software point of view, one would think. So the other thing I have to say for the computer scientists, if there are any in the room, when I say a stencil is bandwidth bound, then people will disagree and will say, no, there are cases where you can implement time integration in such a way that you have blocking and then you're not memory bound anymore. And that's true if you have a simple problem where you have a simple differential equation and just one stencil. But the reality here is these are the Euler equations the COSMO code solves, and I think most climate codes look more or less like this. What I'm trying to show here is here we have many differential operators that implement different stencils. So we have about 50 or 70 in these codes. And then they are intertwined. So we have the physics part, we have the horizontal advection, vertical advection, we have the fast modes, and then we have the water advection. And everything is really intertwined with different length scales that are taken care of in the integrations in different ways. So it will be very, very difficult to impossible to really find a smart, use any of these blocking schemes that are known for say, wave equation and simpler equations in this problem. Okay, so that's why actually we have to bite the bullet with this bandwidth problem. Now, in terms of implementation, and this is where the argument, my main argument is, things really are much simpler than most people who implement climate codes think they are, okay? And that's actually where really the discussion has to be. So in this case, we implement the dynamics in terms of a stencil library. And the stencil library is implemented as a domain-specific language embedded in the framework of C++ template metaprogramming. So we use an existing language framework, but we introduce new semantics. And that supports currently 3D structured grid is parallel over the IJ plane, and I see I have to speed up a little bit. But the main point here, the slides will be distributed, is it is a general library, general language, not necessarily just for climate codes, that we introduce that abstracts the hardware layer. So has different backends for x86 or CUDA, but the user is really doesn't have to deal with this. And we can, as I said before, we can even support different storage order depending on what hardware we're on. So we can try out the different ways of storing the fields. And we use different parallel programming model if we are on x86 or GPUs. And the software architecture then really looks like this. The current code has physics and dynamics. This is a simplified view, monolithic sitting on top of the system, MPI. And now in the new code, we really have now a first domain-specific language here, a tool that can be then used in terms of the dynamics, which is the application tool. And the actual code then sits on top of all of this and can be viewed like a prototyping code. So in the future, today this is the top code here is a Fortran code, but in the future it can be, you can have bindings and operate in a more dynamic language like Python. And the hardware, as I said, is the backends that abstract the hardware. And so the user up here or up here doesn't really even have to know the details of how the implementations work on the different systems. So how does it perform? Well, it's what I'm showing here is on a particular socket, Sandy Bridge or K20X, for reference also the Fermi GPU, a different workload, so different number of columns. And you can see here what actually you expect from implementation and hardware is if you have a lot of work on a socket, then the GPU wins by a factor about 3 to 4, and that's about the difference in memory bandwidth. So no surprise here. And if you have very little work on a socket, then the CPU will do much better. But then you need a lot more, okay? So now we really have two ways of looking at the problem. We can start with the current production problem, which is this workload roughly at 300 milliseconds per time step. And we can now scale it to put much more work on the GPU and still maintain the same time to solution. And then basically use much less resources and therefore energy. Or we can say we minimize time to solution and we go to really the least amount of work we can afford in terms of strong scalability on a certain number of CPUs, and then really improve time to solution, but be ready to spend more resources on it. Okay. Now that really leads to the different ways of viewing a hybrid system. So, for example, on our system at CSCS, we have a blade with 4 nodes, hybrid nodes with Xeon and GK110 GPUs connected to this system on a chip router. And these 4 nodes are either using both CPUs or GPUs at the same time, like HPL would, or a lot of the materials codes. Or they can, the 2 modes I've been discussing before is you can either use just the CPUs or just the GPUs. So COSMO would run in one of these 2 modes, where you then have to pay attention that you put the data in the right place, either distributed over the GPUs or distributed over the CPUs. Now, the last thing I want to show quickly is really summarizing the production problem over a number of production systems. So the current code, blue code, running on the current production system, which is an XE6, Cray XK6 with Interlagos processor, moving the same code on the production problem over to the XC30 to the Sandy Bridge processor leads to a speed up of about the factor 1.3. Okay. If you now move to the new code implementation, you get the speed up of about 1.5. And if you now use the new code, new implementation on the GPUs, and here I'm always comparing the same number of nodes. So I put the problem on a given number of nodes, and then I get the factor 1.5 or about the factor 3 in time to solution. If I go from the current production system to this new architecture, or if I take the new system and move it from the current code to the new code and the GPUs, it's about the factor 2.5. If I ask the energy to solution, that's my last slide now. I'm going to stop. After that, the current production code uses about 6 kilowatt hours. On the XC30, and this is a result of better packaging, it's about a factor 1.75 better. It's about another factor 1.5 if we use the new code. And if we use GPUs, it's so this is really time to solution that is improved. This is really more than just time to solution. So it's about a factor 7, or if I stay within one architecture, it's a factor 4 that I win in energy to solution. And so you have to balance these two things. You have to decide if you want time to solution, and then you push things in a different way, or if you worry about energy to solution, then you push things, use fewer GPUs on this given architecture. So I think I'm going, in the interest of time, I'm stopping here and switch over to the acknowledgement slide while I'm taking questions.
Let's thank our speaker.